So I hear you would like to learn about more involving gas laws. Well, come on over and I'll introduce you to the ideal gas law. Once upon a time in a land far, far away, we have been learning about several gas laws. We learned about Boyle's law and Charles' law and the combined gas law, Gay-Lussac's law. For something like Boyle's law, we have a situation in which we have an initial system with one set of circumstances and a secondary system with a second set of circumstances. So we have an initial volume and an initial pressure and a new pressure and a new volume. In the ideal gas law, we have a single system, which means that system is only one set of circumstances. You will have a single pressure, not a second one, a single volume, a single temperature, and so on. A gas behaves ideally if it conforms to all of the gas laws at the same time. Now, this is a theoretical gas, although real gases do behave this way in certain circumstances. But you being able to identify the exceptions to this rule is outside of the scope of this class, and you don't need to worry about it. By combining these laws together and including the number of moles, one equation can be made. It is called the ideal gas law. The ideal gas law involves things that we've already learned about and a couple extras. As you know from, or this is also called PIVNERT, and it is named for the formula PV equals nRT. Most of these components you're already aware of. P is pressure, which can be measured in ATM or atmospheres, in kPa or kilopascals, and in mmHg or millimeters of mercury. The N stands for the number of moles, which, as you know, is the quantity we typically use, or the unit we typically use when we're measuring quantity of atoms. The V stands for volume. In these previous problems with the other gas laws, Boyle's, Charles, and etc., we were able to use more than one kind of measurement for volume because we had more than one and they were going to cancel each other out. In this, when we're using ideal gas law, we can only use a single one, and that would be liters. So if you're given anything other than liters, you're going to need to convert. T stands for temperature, which, as you know from previous gas law problems, we will always measure in Kelvin. So whatever you're given, convert it. We cannot have negative numbers because we would wind up with negative pressures and volumes. The new component is R, and R is the ideal gas constant. Now, when I learned this in my chemistry courses, I was only given one, which meant a lot of conversions. For you, because I like you so much, I will give you three. 0.0821, and the units on the first are liter atmospheres per mole Kelvin. The second one I'm going to give you is 62.4, and this is going to be liter millimeters of mercury per mole Kelvin. As you've noticed, the only thing that's changed is my unit of pressure. The third one will be 8.31, and this will be liters kilopascals per mole Kelvin. Again, the only thing I'm changing is the unit of pressure, and you'll choose which gas law you will use according to the pressure given in your problem. This means that you don't need to convert every single one of these to the SI, which is the one that I was given when I initially learned this. Now, I have a sample problem for you. When the temperature of a rigid hollow sphere containing 685 liters of helium gas is held at 621 Kelvin, the pressure is 1.89 times 10 to the third kilopascals. How many moles of helium does the sphere contain? The first thing I do with any of these type of problems is write down, what do I know? P, V, N, R, T. In this case, I've got 685 liters. That is a measure of volume. The next thing I am given that I know is 621 Kelvin. The next thing that I am given that I know is 1.89 times 10 to the third kilopascals. So that would be a unit of pressure. And now I have two values that I'm missing. I am missing N and I am missing R. R, I'm going to choose one of these constants. So in this case, since I had kilopascals as my given pressure, I am going to choose 8.31 liter kilopascals per mole Kelvin. And N is my missing value. So that's what we're solving for today. The equation is PV equals nRT, and in this problem we are solving for N. So in order to solve for N, I need to get it alone on its own side of the equation. I'm going to divide both sides by R times T by R times T. The R values are going to cancel out. The T is going to cancel out. And now I have a newly rearranged equation. N is equal to PV over RT. So all that's left is to plug and chug. I will plug in my values, my pressure of 1.89 times 10 to the third kilopascals times my volume 685 liters over, remember to use parentheses if you're dividing by more than one quantity, 8.31 liter kilopascals per mole Kelvin times 621 Kelvin. Now, when I do the magic of my calculator, I get 250.8763669, which is a really long number. I'm going to limit that by my significant figures. I have 1, 2, 3 here, 1, 2, 3 here, 1, 2, 3 here, 1, 2, 3 here. So I'm going to have to cut this off at 3 significant figures. My answer is going to be 251 something, but as we know, a number without a scale is meaningless. I need to go through and look at my units next. Kilopascals I have both on the top and the bottom, so they are going to cancel. Liters I have as well. Those are also going to cancel. Now if you look here, I have Kelvin is in the base of this fraction here, and it is on top here. What I'll be left with is moles. Now in this case, I actually have 1 over moles in the denominator of this fraction, which means I'm dividing by 1 over moles. If I divide by a fraction, it's the same as multiplying by its reciprocal, which means my answer is going to be in mole, which is exactly what I expected it to be, because this is how many moles of helium does the sphere contain. For your pleasure, you will be working on this lovely worksheet of ideal gas law problems. You have 7 of them. You have the hour to complete them. If you are not working on your homework, I will make sure that it is collected at the end of the hour so that I can mark you appropriately. So please do begin your questions in class, and have a wonderful day. Try not to miss me too much. Goodbye. Behave.